Thank you very much, Sander, and thanks for inviting me, as usual. So I'll mention some of the work that we're doing on the topic of ammonia combustion, which is quite interesting because it was something that even in our department people didn't believe in. Thinking, okay, ammonia is being used for cleaning purposes, for fertilizers, but how on earth are we going to use it for fueling applications? And it was everything related to some work that Siemens at the time was trying to do. We have progressed from that quite a lot, and I'll just explain as we go along this presentation. So I have an introduction followed by some challenges, developments that we've been doing on the subject, and then some collaborations that we got at the moment with many universities in different fields. Some of those relate obviously to numerical modeling, which is I think one of the big traits that we want to then get out of this. So this is just some of those, again, bios that you like to read, but in essence is that a few years back, 2013, just before the end of the year and Christmas, we had some people coming from Siemens. It was really fun because a whole table full of people from every different subject. We had people from maths, physics, socials, engineers, obviously, and a few universities across Wales. And these guys from Siemens were all of the idea of using ammonia and burn it. So at the time, the person, an academic that was my manager, Phil Bowen, he looked at me and said, like, okay, yes, if we need to then do this and burn some ammonia, that's fine, but take it as a Cinderella project. I didn't understand at the time what a Cinderella project would mean, but eventually it would be like one of these fairy tales where you just transform into a beautiful princess, get the money, and then after that you realize that just going to convert into a pumpkin at the end of the night. So that's going to then lead you nowhere. So I thought, okay, why not? Let's give it a go. And I had for a long time tried to then find something different to do and burn, because people were already doing hydrogen, they were doing shell at the time, and many other combinations that I thought, okay, I need to then find something interesting if I want to progress on this area of combustion, especially thinking that anything that burns these days, people consider it as a problem for the environment. So again, I took over, and then that produced loads of very interesting and profitable projects. We got loads of research, loads of papers, and we still work on this subject as a very feasible way to reduce carbon emissions and bring some net zero fuels. But as I've said, one of the things that is important is to raise the interesting aspect of all the modeling that we need to do to then develop these technologies. Because at the moment, we have relied on a few experiments worldwide, and I'm talking again about probably 2012-13, that Japanese start doing some of this work. Eventually, they gather forces with all the industries interested in net zero fuels, and now they have massive consortia there in the country trying to then make this happen. But still, we rely on a few demonstrators that require much more progression and resolution. So we can then give data for a few sets of experiments, but to then approach all the spectrum of different possibilities will be impossible if we do it in a lab or experimentally. It needs to be done numerically. So with that, the whole subject goes around the recovery of renewable energies. We know their intermittency, therefore we need to then find some other sources of storage we can use to cover for that intermittency that we experience, especially with wind or solar power. Cases that I have raised over the years go back to things that have happened here in the UK, Australia, the US, etc. There was one case a few years back before the pandemic that 1 million people lost power on a day that we were running at 48% wind. And it was because we didn't have the storage to then cope with that. That happens in the Midlands, and it's something that could be recurrent. So therefore, storage means that we can then tap into some of those resources, then put in any media of, say, batteries, chemicals, thermomechanical storage, pump hydro, etc., and eventually use it as we have that fluctuation in wind or solar resources. So one of those that is always coming back, and we need to address and acknowledge as the one with lots of potential is chemicals that we have used for decades, centuries even. We have methane, hydrogen now these days, and in this case that I'll be talking about ammonia. And interesting is that different to some of these technologies, for example, in case of batteries that can store some of the energy for hours, days, weeks. In the case of the chemicals, we can do so for weeks, months, years, as I've said, centuries even. It was interesting because during the pandemic we had this drum of ammonia, large scale, and we went away, then came back 3 years later. The whole thing was as we left it the first day. So it was, again, really nice, and it just explains some of these potential avenues for storage of this energy. And on those lines, the different councils around the globe have tried to then address what would be the best chemical, the best scenario to then use, for example, hydrogen, ammonia, or some other alternatives. And you can see from the greens that we have all that amount of energy renewable that we can tap into compared to the one that we have right now for natural gas resources that is very localized. So with that, we know that essentially everywhere in the world we can then potentially tap into some renewable and then recover that energy. With that, they have done, in the case of the Hydrogen Council, some analysis on how to then distribute some of that, because we will have locations where we'll produce loads of that hydrogen or ammonia or whatever it is, and then some others, like for example in Europe, where we're going to consume all that energy. So with that, doing some techno-economic analysis, they studied how much it would cost to move from a port to the final destination that molecule. So they discover, and then they did some analysis on the cases of ammonia, the case of liquid hydrogen, and liquid organic hydrogen carriers. And the scenarios they discussed were from Chile to the US, from Saudi Arabia to Europe, and Australia to Japan. And as you can see, probably is, I hope is visible, the costs of final destination are almost the same for all of them, with the only difference that in the case of ammonia, there's a big component that is almost a third of the cost that goes to cracking. Meaning that if we can then remove that cracking, ammonia for those kind of scenarios is the most profitable solution. That's the reason because Japan is already importing some ammonia and use it for coal power stations. The same will happen with Japan, with China, and South Korea is already as well doing the same thing. And here, for example, in the UK, we are now looking into some possibilities, especially for rural locations. So therefore, ammonia can be recovered from renewable sources, can be rescued from stranded locations, enable the use of waste streams that we can get from industry and processes. Interestingly, when it comes to storage, we store it for long periods of time. Ammonia is much cheaper than the hydrogen because of the cryogenics and high pressure we need. Can be used in isolated or island locations. Can be employed as a fertilizer, as it's been meant to be done by last decades, the last century, but it can be used as a fuel. Hydrogen content in ammonia is more than the hydrogen that you get in the hydrogen molecule, because you got 3 atoms of hydrogen in the ammonia molecule compared to 2 atoms in the hydrogen molecule. And then finally, there's a supermassive market of billions, hundreds of billions, that has been moving around the ammonia for over 150 years. So with that, there are many different ways to actually tap into this resource. We've got all the renewables, the ways that we are producing right now, all that hydrogen. And if we can think of a way of integrating, we might go first to have the renewable energy direct into the grid, and that one feeding into the immediate demand that we got for heating and transportation. We want to use some of that energy to store the resources and eventually use them. We can then use that for also transport, heating, cooling processes, propulsion, and stationary power. And if we think about that long distance, very long-term storage, then ammonia could then fit into the same aspect of transport, heating, cooling, and processes.
Sorry,
Yep.
What is cracking?
So cracking is when you split up the molecule. and you have the nitrogen from ammonia and hydrogen, and then what happens is that you end up with nitrogen as a molecule and hydrogen as a molecule. So the ammonia will become then these two molecules, nitrogen and hydrogen separately.
So that costs energy to do that.
Exactly.
So
Exactly.
yeah.
Exactly. And the thing is that now these days, lots of companies are actually working on that concept, evaluating different materials and different processes, ways to then recover some of waste energy that could be tapped into this cracking process, etc. And most of the companies these days producing hydrogen from ammonia or have to do with ammonia in some sense, they are looking into it. So it's a very interesting area of development and research, because most of these systems, they are no longer than this table, and we're now talking that companies are going into scales of an entire factory. So again, super massive systems because of that scale. Just as an example, Germany, the same is happening now as an evaluation here in UK. Germany is going to start importing ammonia from Canada. And that one is going into one of the ports that they got in Brandenburg, close to Brandenburg. And the scale is to, again, in the loads of hundreds of tons of hydrogen annually to feed into the natural gas grid. So then replacing natural gas grid by hydrogen. So to do that, they will require, again, these supermassive cracker units, again, are on development. So there's lots of things still to know, for example, the economics and these new materials that will be needed for those scales, the environment, the regulations. There's no regulations because we have never used ammonia as a fuel. The public perception because it's toxic, and as I said, just got this horrible smell of rotten egg that is just very pungent to the nose, and the reactions and combustion. And the interesting thing, and what I'll be talking about more in detail, are the reactions and combustion, and how we're trying to then use some mathematical processes to then make more efficient our reactions and the combustion profiles that we're analyzing. Because as I said, and if we go for each of the individual cases that we could go for, we'll just spend years trying to analyze a single geometry. So it's not possible. So these are just some numbers related to efficiency that you get in a system, just a comparison between hydrogen, ammonia, methane, that is essentially natural gas, and the methanol. And then if you get them from the renewable energy source and then passing through all the processes, you have around 70% in the final end using hydrogen compared to 24, 26, and 25 for the other molecules. Which again takes us to then being the only one carbon-free, ammonia, the potential solution for many applications. And with that, there are some other studies that have looked into how we use hydrogen or ammonia in different locations, and that will then change the cost of what is the electricity price that you will pay in each of these locations. So depending if you're close to, say, for example, a line that is feeding ammonia into the Midlands or the region of corn in the US, like for example Las Vegas, ammonia would be the lowest cost solution. Whereas if you're close to the sea, offshore locations, wind locations, then Miami, one of those cases, hydrogen would be the most feasible solution. But combining both of them makes the best case scenario for the cases of the economics, because you can then reduce the size of what is your system for hydrogen production, and at the same time the ammonia storage can be reduced that same way. So lots of techno-economic analysis that are now going on in terms of analyzing how hydrogen and ammonia can be used in these promising scenarios. So these are some of those examples where we are now evaluating the use of the molecule in proton exchange membranes, fuel cells, alkalines, solid oxides, internal combustion engines, combined cycles, furnaces and boilers, etc., with all the different efficiencies, challenges that we got, and the strategies to then go ahead and use that molecule. So as part of that, we have identified 4 different challenges. One, that is the production of ammonia carbon-free at a cost reduction efficient production. Power generation scales that require stable and low emission conditions. The public acceptance, that's something that is very important with the safe regulations and community engagement. Regarding the safe regulations, there's a lot of software that has been developed over the years related to risks, but still many of the things that are related to the expansion, leaks, and potential consequence of having different ammonia release quantities are still unknown. And obviously the economics that need to be profitable. So here is an example. Oh God, that doesn't work. Of what happens with the changes, for example, when we look into the fundamentals, what happens when we change that amount of ammonia into what is a flame. And as we change that value, then what is the flame speed of the flame changes drastically. So in this case, we have 100% ammonia. We have a case that involves methane, 50%, and then we have hydrogen. And if we use just pure ammonia, the velocities of that bubble, the way that we analyze these combustion profiles is how fast bubble will expand inside of a confined space. And we'll go from 6 centimeters per second to almost 10 times that value. So you can see that the complexities of changing those values of flame speed are very important for the stability of our process. So for example, we have cases where we are trying to use ammonia with some partial cracking and just traces of hydrogen, then that will change this value and therefore change the stability mapping that we got for a particular system. So therefore, there's lots of things that we still need to understand that we have been doing, as I've said, experimentally, but that require a lot of modeling. And that takes us to what is the reaction mechanism that have been now in trend and people looking at for now probably 30 years. This shows very graphically how the different combinations of ammonia, ammonia-hydrogen, ammonia-methane, ammonia-diesel, etc., can have different values of stability and therefore producing different temperatures and pressures. And each of these squares just shows where we can use one or other reaction mechanism that has been developed over the years. So here, for example, in this case, we got 1, 2, 3, 4, 5, 6 different methods of measuring these values with 5 reaction mechanisms that have been in trend for the last 5 years, and then that trying to then match some experimental that has been put forward by the different groups. And you can see there's lots of different trends depending on what is the mechanism that you want to use, and you can then see it back here where you have some cases, for example, this square will be representative only for a few of the reaction mechanisms that we got available, whereas this one that is in red will be only specific to one of the others that we have in that table. And that just shows how difficult has been over the last 30 years to actually come up with a reaction mechanism that help us to then visualize what is going on with the combustion of ammonia. And the main reason for that is that we got a hydrogen molecule and that nitrogen that reacts very differently depending on its concentration, its pressure, and also its temperature. So those kind of changes are very graphic as well here in this experiment, where you have cases with little hydrogen, and as you increase the hydrogen content, they start producing different process and different stabilities of that flame front that I was talking about. You have cases at pressure and then hydrogen content, and as you increase the hydrogen content and then increase as well the pressure, you start experiencing loss of instabilities in the flame front. Those instabilities as well, we don't understand really what is going on in terms of that hydrogen addition, how that is impacting on the profile and stability of the flame, and it's all been trying to then look into things related to the flame on its own, its diffusivity, thermal, and mass that relates to a number called Lewis number, and then on that basis define if the instabilities are growing or being reduced depending on the condition that we're analyzing. Now all this takes me to numbers, dimensional numbers, dimensionless numbers that we have tried to use to then explain these type of values, but they are not cut to the task. It's a theory that we have been developing over the last 40 years, but still is not giving us the right numbers to then acknowledge what is going on with those type of instabilities, especially when it comes to that nitrogen-hydrogen content that's changing across these blends. And because of that, you could end up with a list of all these different reaction mechanisms and all those different processes to try to understand what is going on with those blends. So these are examples of how changing the amount of air and the amount of hydrogen, the amount of ammonia, will then have different responses to the reaction mechanisms that we're approaching. So here, for example, in this case, we have a scenario that has an addition of air, so it's air-rich, and then we got via error analysis what would be the best reaction mechanism that we can use for those conditions. If we change slightly what is the amount of air, then the one that was at the top has come down here in the middle. And as we go up and then increase even further the amount of air, then that changes as well. So there's no consistency in these reaction mechanisms and how they approach the nitrogen reaction. And again, the only thing that we can do is via numerical methods try to force some of these reaction mechanisms to behave in a way that help us to match and have an accurate correlation to experiments that we have taken. But if we change the experiment slightly, that could mean that we can no longer use that reaction mechanism. So therefore, what we need is numerical models, mathematical approaches that can then make more efficient this type of reaction mechanism. Lately, we have been working with a university in Hungary. They develop a model called Optima++. And as I said, the way that they do it is statistically look into the reaction mechanisms that we got at hand, and then with that run different scenarios, then force those scenarios and the reactions that we got in this mechanism to then try to correlate as close as possible to the emissions that have been measured. But that works for one of the emissions, it doesn't work for the next one. So then the mechanism needs to then go back into Optima, and then with that force it to then the other emission. And then so on, we keep going, and then eventually get as close as possible to the emissions and stabilities that we are measuring. But as I've said, it is a process that still is inefficient and requires very good mathematical approaches to then improve it properly. Some other stuff that we have done over the years to do with direct numerical simulations, and in this case trying to do some of those experiments. So these are all experimental analyses that were used to determine what would happen with a small kernel of ammonia-hydrogen, and then that being changed to the amount of air that we got. So if we have high air content, what would happen is that we start producing those instabilities that you saw in the previous slides. But as we go up and then increase the amount of fuel, reduce the amount of air, then those instabilities go down and the flame profile becomes more stable. We don't know yet why that is happening. And that we can use it to then evaluate as well some other profiles, for example, sprays. Like in this case, we have done some analysis for the penetration, the size of the molecules, the size of the droplets, and the angles of those jets that we are evaluating. One of the things that is very interesting in the case of ammonia is that as we go and increase the pressure, then we keep the consistency of a liquid injector. But if we have low pressure conditions, then what happens is that the ammonia will start vaporizing. That process of flashing still is unresolved. So it's one of the things that, again, are very complex in terms of heat transfer and thermodynamics, that boiling, flashing point that is occurring in there that hasn't been resolved properly in the CFD models that we are using. This is a very interesting subject for further development. Another one that we have tried in terms of fundamentals is the use of plasmas. We have done experiments that using different plasmas, nano repetition or glide arc systems have shown that we can use these plasmas to reduce emissions and control the stability of the flame. Only problem in terms of engineering and the efficiency is that we require obviously much more energy to the one that we're getting out of the system. But in terms of the efficiency of the process, NOx emissions are reduced in almost 10 times. The stability of the flame is properly controlled, and then we go from flame profiles that is just like this, about to then disappear, to then a really nice standing flame. One of the main issues is that we need to characterize the formation of radicals, the production of isotopes, the interaction between these nitrogen and hydrogen molecules, and now the addition of that energy. That, depending on what is the value of the voltage that we are using, will have different impacts on that final flame. So this is another subject that as well requires a lot of interesting modeling, because there's nothing out there. It was probably 2021 when Georgia Tech did the first experiments on ammonia plasmas, and then after that it's been 3-4 years that every university working on ammonia is trying to do, but not many have experimental facilities. And as I've said, the problem is always having the system to then run those plasmas, because it's just very expensive. So for that, numerical modeling could be the best solution to then evaluate and then characterize at different conditions. Some of the work that we have done has to do with internal combustion engines, and we have two internal combustion engines, one in the STFC next to the diamond laser, where we have been doing experiments using ammonia-hydrogen, and this is the project that I mentioned with Siemens. With that, we have progressed, and now we're looking into the use of internal combustion engines for backup power, where we can go to rural locations and then use that to then power the facilities that they got for poultry, for animal housing, for the same process they're running, etc. And then with that, use the ammonia not only as a fertilizer, but also as stationary backup power and for fueling in the heavy-duty trucks that they got on site. So with that, there are a lot of things that are still, again, unknown, and that require a lot of intensive and improved numerical modeling. For example, the way that we're injecting the ammonia, as I've said, we have flashing, but then there are new techniques and new methods that some of our Chinese colleagues have been trying to develop, and this has to do with the way that we're injecting those fuels. So, for example, in this case, you have a normal injection. You have a spark, then ignites the whole process, and then produce the flame and the pressure to then start moving the pistons. Then you have another one where you have higher spark energy system, but then the new one that they are proposing is using very fast jets. As I said, once that you have a change in temperature and pressure, what happens is that in the case of ammonia, many things related to that change in state start happening. And with that, we have seen that improvement in the efficiencies go up, but the problem is that we still again don't understand or are not able to then see what is going on in terms of the numerical modeling, the fundamentals in those processes. These are some changes that they have done as well, changing the orifice of those injectors, and as they change that orifice, then the values of the ignition delay as well tend to change. All this experimental, and as you can imagine, all this analysis took around 6 months to be conducted. Having a CFD model nicely validated would have taken just a portion of that amount of time. So we need more of those models. So that's what some of universities have been trying to do. These, for example, is 2023, just being developed, and they predicted some of these changes as we increase the amount of hydrogen in those blends, what happens in terms of temperature and changes in the piston. And in the same way, they have done some other studies, some other universities, just as well at the end of last year, where they did some studies on the propagation of these gases and atomized spectra that we got with ammonia. Some other things that are very interesting in terms of those numerical models that we have been doing have to do with the heat release rates. Then when it happens, it tends to then be in the curvature of the flames that we are producing, and as we are then doing so, some of the radicals that are formed in the process tend to then collide in these core regions, in something that requires its proper analysis numerically. And the same way that produces in the contact with oxygen, a lot of nitrogen oxides. So we have the high heat release rate being located here, and at the same time, the production of emissions that are unwanted. So we have what we need, but we have as well what we're trying to avoid. How to then deal with that is something that we're trying to find out and then use some more advanced correlations. Boilers and furnaces is another area that we have been doing over the years. We have different aspects of these large-scale processes that have been developed over the last decade, and now these new trends where, for example, cases in Japan, now they're moving from the use of natural gas to ammonia. There was 2 years ago when in Foshan in China, they had the first ceramic tile being produced using pure ammonia, and then with that, they're moving into the production of hundreds over the next decade. In our case, we have been working on the replacement of propane. Lots of rural locations, processes across the UK, they operate using this fuel. And one of the things of most of the suppliers is that they see that business being cut in the next 10 years. Because again, of the situation in Europe and the UK that we're trying to then dephase from the use of fossil fuels. So for that, propane and ammonia, they share very nicely some of the properties in terms of storage. The temperatures that we require to store propane and ammonia are almost the same, 33, minus 42. In the case of the materials that were employed to then feed some of those lines, it's exactly the same thing, carbon steels. We can use them without any problem. And then the only thing that we got to be aware of is that the amount of energy that comes from the ammonia compared to the propane is much less, so we need more ammonia to then feed these propane tanks. But if we're thinking that all that energy that we talked about at the very beginning could be tapped into and then be used to produce that ammonia, then eventually what will happen is that ammonia will be at the same cost of using the LPG, especially with the taxes and the carbon credits that will have to then be paid otherwise. So for that, we have done all these setup. It's a business project that we got, and as part of all the analysis that we have done related to risk assessments, we have controllers that now we're trying to integrate using some of the techniques that we have seen across the flame profiles of using the ammonia and hydrogen. So part of that is all the control system that is going to be talking to the main controller, feeding the fuel and air, but at the same time looking at the flame using artificial intelligence. So via artificial intelligence, we're going to define what is the size, shape of the flame, and at the same time the radicals that we're producing, so we know exactly what will be the amount of air from fuel that we're putting in there. So with that, we can control that flame profile, and then finally the emissions that we're going to be producing at the end of the stack. Similar approaches have been used by other companies, especially in China and in Japan, where they're now using ammonia to remove and replace carbon and coal in power stations. So we're talking about these supermassive power stations where they have now replaced up to 35% of coal by ammonia. And the results are very encouraging, very interesting, but still very, the fundamentals and complexity unknown. This case, for example, shows that a coal molecule that has been volatilized and still producing some of that ash, all that radiation, and eventually start mixing with the gases of ammonia that come in contact with them. Those fundamental reactions, we still don't understand it fully. The way that that radiation is affecting those particles as well is still unknown, and the only thing that we know is that it makes the process more efficient, reduces the emissions, and potentially can be used at up to 50% replacement of coal in these large power stations. So that's the reason, because now China is moving into this context. Most of the publications that relate to ammonia coal come from there, and it's because they want to replace all that coal by ammonia via this way. But again, as I said, one of the things is that we still don't understand fully what is going on there in terms of that thermodynamic process occurring via coal, volatilization, soot particles, and also ammonia gases being interacting all between each other. In the cases of, for example, some burners that we have been designing, as I said, we are looking into the use of artificial intelligence, how we can then integrate that as part of the control systems that we're employing. Some of those analyses have to do with the radiation that we're producing, how we can then increase the amount of radiation, especially thinking about processes where we can use this molecule for steel production, cement production, and also for glass making. And one of the things that is very interesting is that we can then put in context all these artificial intelligence or neural networks to then define methods of stability for these borders. There's a big drawback though, and the problem is that these obviously are based on the teaching that we do to the neural networks. And that depends on, first, the quality of our models and experiments, and then second, the amount of models and experiments we can then carry on. So for that reason, because we can only run experiments, say, for 1 or 2 days, meaning that per year, in the best case scenario, would be able to then run 50 cases, we need to rely on all that CFD modeling. So here you can see some of the results that we got out of 250 different runs that we did just for this particular scenario, changing some of the amounts of temperature inlets, air content, fuel content that we have for this particular burner. And with that information, we've been trying to then feed into that neural network and artificial intelligence to help us out to find equations that can then be used for the controller that will employ to then control the fuel-air-fuel ratios that we're going to be using and the different conditions we require. Now, this is a process that still is very inefficient as well, because we need to then do the running for each of these individual cases, which is not that bad. It takes a day and a half, but still, again, requires all that feeding from here to then the neural network to carry on and then do those studies and defining that trend that we require for the control system. And that's only for the cases of major molecules like nitrogen oxides or the content of onboard fuel. So if we wanted to do analysis on things that have to do with radicals, because we know that there's a lot of potential in using those radicals to reduce emissions and also generate heat release rates at higher values, then that would mean that we need to then increase at least an order of magnitude the time we spend on this feeding from the numerical model into the neural networks, which again requires some way of making this process much more efficient. We have been trying over the last few years with a PhD student to then look into the development of a very simple case using CFD modeling and then feeding that directly into artificial intelligence methods and machine learning. And that has been very successful, but still requires, because everything is based on then getting the hard results from the model and then using some of those numbers back into the machine learning to then get that final solution. We need more robust, more efficient numerical methods to actually do that more efficiently. And we can then integrate these numerical models into these artificial intelligence neural networks in a better way. That will save us, again, orders of magnitude of time that we are now wasting to then understand what is going on with these systems. Gas turbines is another area that we have been using and then developing over the years, again, going back to the Gas Turbine Research Center in Port Talbot, and it's got to do with, again, how we can burn this ammonia in different conditions. One of the things that we always find is that as we increase the amount of fuel, we start producing more and more hydrogen. So as part of that cracking process I mentioned, what happens here is that at the flaring front, we are now producing hydrogen that can potentially be burned in a secondary zone inside of a combustor. So with that, we can increase the amount of energy that is being produced while making these systems more efficient and less pollutant. And as part of those studies, we have looked into radical formation, and these are different cases that show the content of natural gas, ammonia, and hydrogen, and how, depending on that value, they will produce different radicals. Those radicals have some correlation Again, we're still trying to then study that correlation and find out what is the perfect one, because most of the cases that we have done, again, are very punctual, are just based on two geometries, but we require more. And that whereas we get all these analysis, numerical models, and CFD that can be implemented into doing so. Because if we get to know what is that correlation, we can then create tables like this, and as well correlations between those radicals to then define stages of stability. So here, for example, we have been used some spectrometers. Spectrometers, depending on the amount of ammonia that we are using, will give us different trends for all these different radicals that we have studied. But then interestingly, is if we do ratios between these radicals, we'll get some trends that are some of them linear and that are very critical for what is the radicals that we are forming in there. So we have the cases of, for example, OH, that is extremely important, NH2, that is as well very important, and NH as well shows very nice consistent trends. But this, again, only problem is that we still rely on one geometry to then get us that. We cannot use this at the moment as a general expression for any burner that is out there using ammonia. So we would have some way of making this more efficient and again more general. That would be brilliant, with equations that allow us to then make this a general expression for any burner using those molecules. So we have tried something around those lines, trying to then make more efficient our CFD modeling. We have tried 2D modeling, and then with that, splitting up the flame in different sections, depending on the temperature and there's reactivity. Then main issue is that it only works for very specific scenarios so that we can validate with experiments beforehand. So we still cannot extrapolate these values for a more general expression. Similarly, we have the issue with thermoacoustics, and another one that is quite interesting is when it comes to the turbulence that is generated in this type of burners. Because we use a lot of swirls, and different values are swirling strengths, then we believe that some of these molecules that are produced that lead to emissions like nitrogen oxides, then are formed in these vortex that are just created passing the flame front. Main problem is that as well, then the resolution of the CFD models giving us those values is not good enough, and the values for the reaction mechanisms that we're employing will not provide us that accurate resolution that we would expect inside of the recirculation zones. They work nicely when it comes to a very simple scenario, but as I've shown you, once you change that value, then it could then fall out of that condition that was designed for, and if that's the case, then the validation is lost. So again, things like the combination of turbulence with reaction mechanisms and heat transfer via these processes, making them more efficient and less computational intensive, would be ideal for us. That was something that some colleagues in Baker Hughes tried to do a few months ago. So this is a study they did in the combustion department. So they were using our burner, and what they tried was to implement a user-defined function in the process of resolution of the flame. So all this part that you see here up to this point, that is internal to the flame front, we use some of these reaction mechanisms that is all in the literature, and then passing that point just at the highest peak of our NOx emissions, they use a user-defined function based on the results that we were getting from experiments. And the results that we got changing those conditions of pressure and also air-fuel ratios were pretty good. Only problem was that the user-defined function was good enough, again, within those values that we had already inside of our neural network that were used for validation. Trying to extrapolate was a big problem. But it showed that using partially some of these analyses and reaction mechanisms in some of the parts of the flame, and the user-defined functions defined by experimental validation or artificial intelligence would be just the solution that we're after. That could be as well used for materials. The interaction between materials and flames is extremely complex. We don't know what happens when we have loss of this hydrogen being embedded into the materials. They will start producing hydrogen embrittlement, but eventually with the nitrogen, it will then produce as well nitration across the surface of the materials. So how that nitration combined with hydrogen embrittlement is going to affect the materials, we don't know. We need more mechanism and better resolution in the CFD model to actually look into those more fundamental analysis. And finally, another topic that is quite interesting, health and safety. So this is what would happen if we had an exposure with ammonia. Ammonia loves water, meaning that if it gets in contact with the skin, it just starts drying up and then eventually kill it. And the problem with ammonia is that if it's pressurized, then once that is released suddenly into the atmosphere, cool down, and then with that produce a mist that can be deadly. So that's the main issue. Another problem that is not that recurrent, but again, we're talking about fertilizers, not fuels, is that it can be explosive because finally it is a molecule that can be used for energy purposes. So for that, there are many studies that have looked into the use of ammonia and that being compared to oil spills. And the final values that they came up with is that an oil spill compared to an ammonia spill would be almost the same in terms of the impact that it will cause on bacteria, plankton, invertebrate, reptiles, fish, and birds. With the biggest difference between them being birds, that will have more impact on the oil spills because again all the covering that they will get, and in the case of the fish, the change in pH that will have a direct impact on these life forms. However, along those lines, some other studies have looked into the dispersion analysis. This is very simple. So they did a study where they compare what would happen if we had gasoline spill and ammonia and another one from LPG on the same station. And this goes into a station located in Norway. So with that, they found out that it was a gasoline spill. There would be barely any problem compared to then what would be the ammonia, and then finally the LPG that could be a massive impact in terms of the probability of fatalities because of the explosivity of the propane. So with that, these models, they require a lot of improvement because they are very simple. They just create and generate a very simple scenario where there's a sphere that is then confining all these gases and then eventually producing these impacts. Similarly, we have some other studies where the total number of premature mortalities can be assessed, and that as well requires better mathematical methods. They use the ones that are conventional for CO2 NO emissions, but there are some other molecules that come from ammonia that are not included in this software. So with that, we have seen that some cases are comparable to those that are now being produced using diesel engines. But again, this needs to then be improved because many of the molecules that are used in this software are not in the final totality of ammonia molecules that can be produced as pollutants. This is, for example, one of those cases where we did such an analysis, and then what we did was to then determine what was the dispersion area of an ammonia drum that we got in engineering. As you can see, that is a very simple circle, and then with the radius changing depending on that total parts per million that can have an impact on the facilities and nearby locations across Cardiff. This is again very simplistic and then requires much more improvement in terms of that risk analysis. Some of those studies been done just recently, a few months ago, try to then address that point and then see how a dispersion of a cloud of ammonia could then change its position, location, and also concentration depending on the air and the conditions of the particular scenario. But this, again, is very simplistic because in, for example, cases like the open sea, we would have air and wind coming from all different locations, and you will have changes in other parameters in the weather that just makes this case an idealization of what would happen if an incident happens. With that, ammonia is now in the talks of people like Boeing, NASA, power stations, as I've said, in China, in Japan, gas turbine for Mitsubishi, and then new boats and ideas that are looking into the production of the molecule of C and then eventually being discharged to other boats across the ocean so they can then be moving around without even touch land. So with that, there's a lot of potential of working on the subject, and there are many things still to be done to actually do it properly. So again, in terms of numerical modeling and all the different equations and approaches we need, the more efficient systems and ideas that we can come up with will help us to then get to the best solution, not only in terms of the reduction of emissions, but also in terms of risk assessment and use of the molecule for reduction of costs. And these are some of the universities we work with and also companies on different subjects, again, that I have approached. And with that, I think that's it from my side. It's a fascinating topic. It's a great area of research and development. There are many things still to be resolved, and we need more and more numerical models to help us out to then get this faster. So yeah, so that was it.